Let's talk now about infinite series, which we simply call series. A topic you probably learned about in calculus, where, like everything else, you were told the basic facts without the proofs and explanations, just the stuff about what and how, but not why. A series looks like an infinite sum, but there are subtleties when it comes to having infinite versus finite sums. Students in our calculus sequence seem to have difficulty dealing with this topic. I can't speak for every student's individual source of confusion, but I truly believe that students simply overlook the most basic fact that when you have a series, you really have two distinct sequences. There's, of course, the sequence of terms of the series. Those are the values that you're adding. And then there's also the sequence of partial sums. The nth partial sum is the sum of the first n terms of the series. In my experience, some students just never were able to get over the simple fact that there are two sequences here. Please stop and let this sink in, or everything else after this is gibberish. In my first expression for a series, I indexed the terms starting at n equals 1, but there are other cases where we really want to start indexing at 0 or 2 or -1 or somewhere else. This is just a notational issue, since the n is used only to indicate which term we're referring to. In this second example, our index starts at 0 instead of 1. Also, we have used I as the index rather than n. Once again, this does not change the meaning of the sum. On the bottom line, we have the sum of ai as I ranges over the non-negative integers. So this translates as a0 plus a1 plus a2 plus a3 plus ... Some series have a numerical value and others do not. The first question in analysis is, given a series, a numerical series with numbers as terms, whether or not the series converges. And if so, what is the limit? That would be the second question. What's the limit? When we ask if a series converges, what we're really asking is whether the sequence of partial sums converges. If so, then the limit of the partial sums is then the value that we assign to the series, and we say that this series converges to that number. So we say if the limit of the partial sums is L, then we say that the infinite sum or series is equal to L. Later we'll talk about other kinds of series where the terms are not simply numbers, especially we can have a series of functions. But for now, our terms are just real numbers. And so the partial sums must be just numbers. If the series converges, then its limit, which is the value for the series, is again just a number. There are several important series that you know, like the back of your hand, you need to know. One is a geometric series. What makes a geometric series is the property that any two consecutive terms in the series have the same constant ratio r. In other words, each term of the series is r times the previous term. We can also talk about finite geometric series, but typically, as I indicated, the series we'll have to deal with are infinite, meaning they have infinitely many terms. The nth partial sum of the series, this geometric series, has a very explicit formula, which you can prove this formula by induction. And it's easy to see when the series converges using this formula. In other words, when the partial sums converge. We have convergence if and only if the absolute value of r is less than 1. This is, by the way, only true when we have the requirement that a is not 0. The first term of the series is not 0. If a were 0, then all the terms of the series would be 0, and everything would become trivial. We ignore that case we don't consider it to be a true geometric series because then we couldn't even define the ratio of consecutive terms. Here again is how we write the sum of the geometric series. It's just the limit of the partial sums, assuming the limit exists. Another very important example, which you should also know like the back of your other hand, okay, is the harmonic series. Here the terms are the reciprocals of the natural numbers. A very important fact is that the harmonic series diverges. Please note that although the sequence of terms goes to 0, the partial sums get bigger and bigger without any upper bound. As I say, the harmonic series diverges. You need to be thoroughly convinced of this, not just write it down as some dubious fact in the corner of your head or some kind of mystery that you have to figure out at some point. You need to really understand this point. So let's go over it. Here's one way to see that the harmonic series diverges. After the first term, group together the next 9 terms, then the next 90 terms, after that the next 900 terms, and so on. The sum of the 2nd through 10th terms exceeds 9 over 10, because you're adding 9 terms, each of which is at least 1 over 10. The next 90 terms, again, add up to more than 9 over 10. The next 900 terms after that, they again add up to more than 9 over 10. And the next 9,000 terms after that, again, more than 9 over 10, and so on. So adding more and more terms, the partial sums can be made as large as you want. It takes a long time to get there, but it eventually does get bigger than any number you name. So it's true that the partial sums diverge, only very slowly. In fact, the nth partial sum is close to natural log of n. This is a fact which follows by considering the integral of 1 over t on the interval 1 to n. You take Riemann sums with unit subintervals. So this formula gives another explanation why the harmonic series diverges. But our first proof of the divergence of the harmonic series is more elementary. And so you should be compelled to believe this as a fact. This example now is a little different. It's known as the alternating harmonic series because we're taking the usual harmonic series, but you're sticking in alternating signs, plus, minus, etc. This series converges. It's not hard to convince yourself of this by the following heuristic argument. It's the idea behind the proof. It can be made into a rigorous proof using the least upper bound property. Start with the first partial sum, that's 1. Subtract a half to get the second partial sum. Add a third. That gets you up to the third partial sum. It's not all the way back up to 1, a little bit less than 1. And then you subtract a quarter to get to the fourth partial sum. Add a fifth. Keep going. Subtract a sixth. Add a seventh. And subtract an eighth. You get the idea. You're stepping alternately forwards and backwards on the number line, but with smaller and smaller size steps. And you can see that the even-numbered partial sums form an increasing sequence, while the odd-numbered partial sums form a decreasing sequence. Both the even-numbered and odd-numbered partial sums are bounded, so they both have limits by the least upper bound property. But they also have the same limit, since the gap between the upper and lower sums is tending to 0. In fact, the series converges to natural log of 2. That's approximately 0.693. But we don't need to know that here. So we're not going to take time to justify that fact. A very important fact, which is easy to check, is that if a series converges, then its terms must go to 0. In other words, if the terms of a series do not go to zero, then this series must diverge. That's the contrapositive of our theorem. Probably the more useful form if you're careful with the negative phrasing of the word diverge. So please do not mistake this statement for its converse, which, as we know, is false. If the terms go to zero, that does not mean the series converges. So the terms can converge to zero, but the series does not converge because its partial sums wouldn't. In that case, just look at the harmonic series as an example, which should be burned into your mind as a reminder. Always try to remind yourself to be successful, you need to learn not just the theorems, but also the examples. It's the examples that will help you avoid the common pitfalls, which are there at every turn. To prove our theorem, let's denote the nth partial sum, as usual, by Sn. Note that each term of the series is a difference of two consecutive partial sums. So you get from Sn to Sn plus 1 by adding An, solve for An. An is therefore the n plus first partial sum minus the nth partial sum. Our hypothesis is that the series converges. That's to say, the sequence of partial sums converges. Let's say to L. Now, using our rules for limits of sequences applied to the identity on the previous line, both Sn and Sn plus 1, they have the same limit, L. So, the limit of An is L minus L. That's 0, and that's our proof. I'm repeating myself here because this does bear repeating. The converse fails. Keep in mind the harmonic series is a reminder. Now, let's look at what happens to a series when we change the terms a little bit. In the first example, we have a geometric series according to our formula that converges to 2. You would expect that by subtracting 1 from both sides, you're effectively canceling off the first term from the left side. That leaves a convergent series, which, by the way, happens to be another geometric series. And you have, again, the formula to tell you that it converges to 1. But we can see this by a different argument. The reason it works in this case, we are subtracting 1 from all the partial sums. So by our algebraic formulas for limits, this lowers the entire limit by 1. And we can repeat this process by taking away any finite number of terms from the start of the series. If we do that, we'll change the limit by a predictable amount, but will not change whether or not the series converges. If you insert or delete a finite number of terms to a series, the new series will still converge, if and only if the original series converges. Of course, you also change the limit in the process. Here we've modified the original series by interchanging the first two terms. This does not change the value of the series. You can similarly permute a finite number of terms of the series, meaning to change their order. By doing so, you haven't changed the convergence property of the series. Also, you haven't changed the limit. And the reason here is that after a finite number of terms beyond some point, all the partial sums will be exactly the same as they were before. Now, the last two examples of modifying series are what we call rearrangements of series. They're rearrangements of the original series. They're obtained by permuting the terms changing the order. Now, a rearrangement can involve permuting a finite number of terms, but you also have rearrangements that permute an infinite number of terms. And then it really becomes an issue. If you rearrange a series by permuting a whole lot of terms, like an infinite number of terms, then have you changed the limit? In fact, is it possible to rearrange a convergent series to get a divergent series, or vice versa? And the answer is yes. We rearrange infinitely many terms. We can change a convergent series to divergent series, or the other way around. So we'll get to an example of that in a couple minutes here. Another example, the harmonic series, we know that converges. If we lose the first few terms, you know you're still going to get a divergent series. So if you permute the first few terms, we also don't change the fact that the series diverges. This last series is another example of a rearrangement. Once again, we've only permuted finitely many terms. Other than simply inserting and deleting terms or rearranging, that's permuting the terms, there's another process of modifying series that can also change the behavior of the series. That's by inserting or rearranging parentheses. In our first example here, the first series shown, the series is really 1 plus 0 plus 0 plus 0 plus 0 plus dot dot dot. And that converges to 1. And the second series is really 0 plus 0 plus 0 plus 0 plus 0 plus dot dot dot, which converges to 0. Both of these series converge, but they have different sums. So there's no reason to expect them to have the same sum when you start rearranging parentheses like this. The associative law for addition tells you what happens when you reparenthesize a finite sum. This is not a finite sum. So the associative law does not apply. In fact, it's not even a sum. It's a limit of a sum. It really is different. Different animal. Both of the series above arise from parenthesizing the alternating series 1 minus 1 plus 1 minus 1 plus 1 minus 1, dot, dot, dot. This alternating series diverges because its sequence of partial sums is 1, 0, 1, 0, 1, 0, 1, 0, dot, dot, dot. That's a sequence of partial sums which does not converge. So in addition to inserting or deleting terms, or permuting terms, we have another operation which is inserting or redistributing parentheses. We've already seen that by doing infinitely many such changes to a series, you can expect to drastically change the behavior of this series. Doing a finite number of these modifications doesn't, but an infinite number of these changes does change it. So far, we have considered rearrangements which permute only finitely many terms of the series. To see what can happen when you start permuting infinitely many terms, let's consider this alternating harmonic series. I'll call it S. We have gone over the fact that this series converges. Now let's start rearranging terms. Actually, it's not explicitly rearranging, but it turns out to be equivalent to the same thing. So let's look at a very simple-minded thing. We're just going to divide the original series by 2. That gives this alternating series, which converges again to S over 2. Now I'm going to add these two lines, and that should give me a series for 3S over 2. What do we get on the right-hand side? Well, we immediately see some cancellation. So what's left on the right-hand side? The first term there on the right-hand side is a 1. That survives. Next, we see 2 terms minus 1 over 4 on the right. They combine to give minus a half. Now let's carry down the plus 1/3 on the right-hand side. Next, look at the 2 minus 1 over 8 terms. I've highlighted them in red. They combine to give minus a quarter. Next, carry down the plus 1 over 5 term. The 2 minus 1 over 12 terms combine to form minus 1 over 6, followed by plus 1 over 7. The two terms of minus 1 over 16, they combine to form minus 1 over 8, followed by plus 1 over 9. And so on. If you keep following this process that we've started here, what emerges on the right-hand side is exactly the series S that we started with. That's our alternating harmonic series. So I can write it equals S. Now we have 3 halves S equals S. But there's a contradiction, right? If you solve this equation for S, the only solution is S equals 0. That's not correct. We actually know that S has to be between a half and 1. I told you the true value is about 0.693, but at least you can be convinced from what we said before that S has to be between a half and 1. It has to be positive. Can't be 0. So where is the mistake in our argument? Well, actually, there are a couple of points at which we cheated. But let's just highlight some of the obvious flaws. The last alternating series required permitting some terms around. Look at the 2 minus 1 over 16 terms that come way after the 1 over 9 term. So the 2 minus 1 over 16 terms, they land way past the plus 1 over 9 term. We move them forward to write minus 1 over 8 before the plus 1 over 9. So that's rearrangement. And when we put the 2 minus 1 over 16 terms together, we were actually reparenthesizing. That's another no-no. If you do infinitely many things like that, that's a no-no. That's when it becomes problematic. Maybe you can look at the earlier steps of this argument and also find other problems that I haven't explicitly mentioned here. Much can be said about what is going on here with these examples and why perhaps they mystify, why they confuse you at first. But before I say more, what most needs to happen is for you to think about these examples. Just think about them. Think about the evident contradiction. Try to resolve them in your head. Allow the examples to sink in, not just the theorems, but also the examples. They inform you to help you adjust your understanding of reality. Trust me, there's no true paradox here. There is no inconsistency in the mathematics. Okay, mathematics makes sense. From time to time, we stumble across something unexpected. Maybe something which doesn't jive with what we thought would happen. Rather than throwing it out, you need to embrace it. You need to face the fact that your expectations are wrong. Probably based on some superficial or flawed thinking about reality.